Oh. Alright. Consider the following recursive function as intended to add a list and a linked list. Void pushback. Probably change my freaking. Can I? Stream settings maybe? How do I edit the. Right? Done it before. There we go. Alright, we're good. Oh, shoot. Alex. Okay, void pushback. Diagram the execution of the call pushback, head 10. Does this function work? Explain using your diagram, 20 words or fewer. Okay, so cur next. Okay, so the first call is going to be void pushback. Why is it? Yeah, that's my cursor. Void pushback cur value if cur equals null pointer. Okay. Okay, so cur is gonna start here. It's gonna start there. I'm gonna use a different color. It's gonna point to this node, and then the if statement won't trigger because cur is not null pointer, so it'll push back to next. It'll push back to cur next. Cur next is here. And then cur is still not null pointer, so it'll push back again. And cur is not null pointer, so it'll push back again to. Let's see. It'll point to like null pointer, right? It'll create a new node, 10. And this will be null. But because cur is pass by value and not pass by reference, it creates a copy, right? But it doesn't update head. It only updates cur. So there's no arrow here. It won't update the actual list. So function doesn't work because its path by value doesn't update head, only a copy. Consider the following recursive function: void destroy list node head. If head is equals null pointer, return nothing. Node next equals head next, delete head, destroy list next. Sparky argues that this function doesn't work because the function takes pointers by value, passed by value, and the pointer being destroyed is only a copy of the pointer being passed as an argument. Is he right or wrong? Explain with a diagram and 20 words or less. So what's happening is, let's see. So I'm going to assume we have a list. I'm going to call it list. My handwriting is terrible. Let's just do easy. Let's just do like 1, 2, 3. So 1, this will point to another node. This node will have a value of 2. And then that'll point to another node. Oops. Too big. And this will have a value of 3, and this will be null pointer. So when this function is called, I have another color maybe dark blue, sure. So head, that's way too thick. So head's first gonna point to this node. If head equals null pointer, return, but head's not null pointer, so node next, next, and that's gonna point to head next, which is this node. It's gonna delete head. Can I add another? Okay, I can't. But it's gonna delete that. And then it's going to destroy list next, which means that head will now point here, next will point here, and so on. So it's going to delete this, and then after that, head will point to this node, and then next will point to nothing, so it'll be null pointer, and then it'll delete this node. And even though it's passed by value, it still deletes it because the copied pointers still point to the original nodes, and it'll still delete them. So explanation. He is wrong because the copied pointers still point to and delete the original list. Okay. Consider the following copy constructor that Sparky implemented for Project 3. linked list, const linked list other, node other cur equals other dot list underscore front, while other cur is not null pointer, this pushback other cur value, other cur equals other cur next. The project guide required that the linked list copy constructor take at most O of n time to copy an n element list. Does Sparky's implementation meet that requirement? If not, what's the most accurate big O of its actual runtime? Explain in 20 words for you. Okay, so this is just an O of n problem. So we're just looking at the function node other cur equals other list at front. Then I'll take O of 1 time. That's just a constant function. This condition will take O of 1 time because it's just comparing other cur to null pointer. This pushback other cur value. So pushback inserts the node to the end of the linked list, and that will take O of n time because it has to iterate through the entire list. Okay, I can. So what I'm gonna do is I'm gonna increase my mic volume but talk quieter. Hopefully that'll make the stream better. I didn't even know I could do that. Okay. Yeah, that's way better. And then I can do that. I'm actually gonna increase it to 15, so it's gonna be so I don't have to talk like nearly as loud. Okay. So yeah, pushback is O of n because it iterates the entire list before inserting the value, and then other cur equals other cur next. That's O of 1 because that's just a constant function. And then even though this line, this pushback's O of n, it iterates through the entire list because it's in a while loop. So this while loop iterates n times, and then we just multiply O of n times n, and that equals O of n squared. So this function is O of n squared, and the copying constructor should take at most O of n time. So Sparky does not meet the requirement pushback takes O of n time and the loop iterates n times. Okay. Oops. Consider the following implementation of the copying structure for the R vector class: R vector const, R vector other, this capacity equals other dot capacity, this size equals other dot size, this data equals other dot data. Assume that all the other functions of the R vector class are implemented as shown in the vector. Here are some possible outcomes. The two R vectors will have different contents. Program that uses copying structure will leak memory as a result. Program that uses copying structure will have address sanitizer reported double free as a result. The copying constructor is completely correct and can be used with the with an appointment of no errors, which is above is most accurate to justify your answer in most 20 words. So it's gonna be this one, because copying the data is a shallow copy. Deleting one set of data will delete the other set. Okay. What is the most accurate big O of the runtime of the following function with respect to the input n? Explain your answer in at most 20 words. Okay. So let's just go through this. Int sum equals 0. It's just going to run O of one time. That's just constant. All of these expressions are O of 1. So O of 1. If I%5 is not equal to 1, that's also O of 1. This sum of 1, or incrementing sum is O of 1. This is O of 1. This is O of 1. And then this is a loop, so we have to find out how many times it iterates. Oops. So let's see. So it starts at n, and it's checking, and it's decrementing I until it's greater than or equal to 0. But if I is... So if I is not divisible by 5, it increments sum, but if it is divisible by 5, it breaks out of the loop. So that means the loop can only run at most 5 times. And because 5 is a constant number, this loop can only run a constant number of times. So we'll just say O of 1. And because it's all O of 1 multiplied by O of 1 is still O of 1. So the most accurate big O is O of 1, because the loop runs at most 5 times. What is the most accurate big O of the runtime of the following function with respect to input n? So it's another O of n question. Int sum goes 0. That's O of 1. This is O of 1. This is O of 1. Incrementing sum is O of 1. This is O of 1. This is O of 1. And this is O of 1. We're going to look at the loop. How many times does it iterate? So if int I is equal to 1, well, I starts at 1. It's checking that if I is less than or equal to n times 2, and it's going to increment I. So that's going to be n times so far. And then it's going to set j to 0. It's going to check if j is less than n. It's going to increment j. So that's also going to run O of n times. So O of n times O of n. That's going to be O of n squared. And O of n squared times O of 1. The thing, the slowest time complexity in the for loop. That's just going to be O of n squared. And this is going to run, so k starts at 1. It's going to check if less until the for loop's going to end once k is equal to n plus 2, and it's going to increment k. So it's going to run O of n times O of n times O of 1 is just O of n, so that's fine. And then O of n squared means we can just ignore O(n) because O(n) squared is a slower time complexity. So the whole function, the big O, is O(n) squared because the inner loop is O(n) and the outer loop is O(n), then O(n) times O(n) equals O(n) squared. Okay. One thing that we might want to do is reverse a map, create a new map that goes from value to key, write a function that does this. Okay. So first, the return type. Let's write in blue this time. Can I write small enough? So this is going to be not an S. What am I doing? It's going to be a map. Let me zoom in a bit. And by a bit, I mean a lot. Okay. Okay, so it's going to be a map. Hold on. Let me make this less thick. There we go. So it's going to be a map. It's going to be a string. And then it's going to map to a set of strings. So that's going to be the return type. And we're returning result. So result also has to be a map. And it's going to map a string to a set of strings. Okay. And then we're just going to iterate through the map, it seems. So there's two ways to do that. It's just we can do const auto. So const auto ampersand let's just use K for the key and then V for the value. And I think that should be good. And then we need to insert that to our reverse map. So we need to insert the key as the value, and the value is the key. So we use result, and then at the key, and the key of the reverse map is the value of the regular map. So we're going to do at V, which is the value, and then we're going to insert into the set of strings. So we're going to insert K, and then return result, and that should be good. Additionally, explain your chosen return type. The return type. Oh my god. The return type is map string set of strings because keys must be able to map to multiple values. Okay. Implement the resize function from our vector, which will double the capacity. Okay. So class our vector and data size capacity. Okay. Int new data. So this is the int pointer. So I think we're just allocating memory. So new int. And it's gonna be this capacity. And then 4. So we need to update. Okay. So for const auto address and ampersand. We'll just call this I don't know, num in data. There should be a space. Oh wait, no. We need to do it the classic way. Okay. So this is the classic way. Size t a equals 0. A is less than. We need to save that value, don't we? Oh wait, size didn't. Okay, size didn't. Okay. Size didn't change, so we can use size. So a is less than this. Size. A plus plus. And then new underscore data index a equals this data at index a. And that should copy all the values, and then we just need to delete this data. Then set this data to new data. And that should be it. First, the following scenarios which ADT would be most appropriate. You're running a website to handle ticket sales for all events or concert conventions. To avoid overloading server, you might want to make sure that only a few users turn a ticket at once. That means you'll need to mix them to wait their turn. So wait their turn, they're in a line, they're in a queue. So queue. The first one in the line. First to check out. Oh, there's a box there. Oh, I guess it doesn't like the box. What's happening? Doesn't like moving it to another page for some reason. There we go. Generally, ticket sale, tickets for a specific seat area. The ticket checkers are naturally going to be able to find information about a specific ticket. Hmm. Um, okay. So this is going to be a map because we want to map a ticket, or we want to map a ticket, yeah, a ticket holder which is the key, to a seat, which is the value. Okay. In the lead up to the ticket sale date, people will check the website frequently. You like to keep a record of all that website accesses and views. So we want a vector because it can hold multiple the same okay. The same people will visit the website multiple times, but unique visitors the website have. So it's going to be a set because it does not contain duplicate values. You quit your job writing ticket sales website to write text editor and implementing the undo operation, so that's when we want to stack because the last change is the first to get removed. In project 1, you wrote a function called apply sub cipher that included a given string with a substitution cipher on that product representing the cipher with a vector. However, we've now learned a more appropriate AT to map. Suppose we had a map char called cipher with the following entries. Map charge on a cipher equals a pair of A to B, B to D, C to A, D to C. We'd like to write a function use a map chart in string, simplify the problem. Don't worry about converting uppercase. If the character is in the map, don't substitute and just use the character directly, e.g. comma space and Z would remain so with the map. Some examples given below. In this case, private below, implement this version of the applies the cipher function. Take cipher as a const map, apply substitute to the string s. Okay. So we want to iterate through s. So for const auto ampersand c and s if map dot count. So if the map has c, oh, not map, it's called cipher. If cipher dot count c, and because we're working with C++, 1 is the same as true, so that's fine. OSS, we want to append the value of cipher, so cipher dot at C. And if it's not in cipher, not in the map, we just want to add the character itself, so just C. And that's it. Okay, good. You have a list of names that are created in a vector of strings, names. We'd like to check the number of times any names appear the name. Suppose that names has the following contents: Alice, Bob, Alice, Charlie, Bob. Then we would like to use an ADT and build in such a way that would let us know that Alice appears 3 times, Bob appears 2 times, Charlie once. So it's like called build counts as just that. So we probably want a map here that maps a person to the count. So map, we're gonna map a string to an unsized integer. Are we returning counts? I think we're returning count. Yeah, return count. So it's just the same as the return type. So map a string to an unsized integer. And then for each name and names, so for const auto ampersand name in names, we're going to do something to counts because we're returning it. And then at name, we're gonna increment that because the default value is 0. So if name isn't already a key in counts, it'll make a key in counts and then set the value automatically to 0 and then increment. So it becomes 1. And then it returns counts once the for loop is done. For each of these, what is the big O question? Bubble in one choice. Okay. So it's just asking what is the most accurate big O. Okay. So O1. This is O1. This for loop is O of n. This for loop Oh my god, I didn't even check anything. This for loop is O of n squared, for the whole thing. Because we're just multiplying by n. And this is O, or this is O of 1, which means the loop would be O of n. O of 1. So the whole function would be O of n squared. So this black. Why? Because the outer loop is O of n, and the inner loop is O of n, O of n times O of n equals O of n squared. Okay. O of 1, O of 1, O of 1, O of 1, O of 1. This is just the same question as before. So O of 1. Why? Because the loop runs at most 5 times. ThinkPad Part 3, where you implement a simulated list, only list size and list front members. Sparky is doing Project 3 and writes this copy constructor. What is the most accurate big O for the runtime of this copy constructor in terms of dollars? Okay, so it's another O of 1 or O or big O problem. So this is O of 1. 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 Or using lowercase n case file. Does that make sense to this one? Of course it doesn't matter. And the while loop is multiplying by n. So this becomes O of n squared, and the whole thing is O of n squared. So O of n squared, y equals push back is O of n, and the while loop is O of n, O of n times O of n equals O of n squared. Int d int n. Okay, another big old problem. This is O of 1. This is O of 1. This is O of 1. And the for loop runs, let's see, I starts at 1, stops when I goes n, or I is greater, okay. It runs while I is less than or equal to n, and then I is multiplying by 2 every time. So this would run log of n times, so this would be O of log n, and the whole thing would be O log n. So this one, oops. Yeah. Part 3 implemented like list class. First class we implemented a find function receives an input value and searches for its value in the list and returns the index of which its value is found in the list. What is the most accurate big O for the runtime of find in terms of n if the size of the list is n? So that would just be O of n. Why? Because we iterate through each node to find the value. There are n nodes. Sparky has implemented in our vector class, like the one we're doing lecture, for printing debugging, you guys implement a function called printVec outside our vector class that will print the contents of the vector. After executing the following main function, Sparky sees a weird address sanitizer error. The address sanitizer error is a double-free error with our canvas. We did implement the structure head TA ticket. Explain why the error is functioning using a diagram. Okay, so this double free most likely means it's a copy constructor doing a shallow copy. So let's just make another fake linked list. So let's just have this. That's way too long. Let's just make this like 69, and that points to 420, and that points to 77. That's 27. Whatever, 27. And that points to 77. And that's null pointer. So we're gonna do, so this is head, and that's gonna point there. And then let's do copy, and that's gonna also point there. So this is gonna be copy constructor. Is shallow. So deleting one pointer's list. Delete the other pointer's list because they point to the same list. Fix use deep copy instead. Here's the following implementation of the copy constructor of our vector class. Our vector disk capacity equals other capacity to size equals other disk size to all the functions are put from like here's possible outcomes. It's gonna be that one. I mean, I already did this question, so I'm just gonna same. For this question, use the following node as definition struct node, or struct node has in data and then a next pointer. Begin with the following linked list. If a line of code will error, explain the error in one sentence next. Following first line. Draw the result of state though. Link list in the box below. Show both temp and head. So head, that's gonna point to 5. That's gonna point to node 10. That's gonna point to node 15. And that's not gonna point to anything. That's gonna be null point. So node temp is equal to head, next, next. So this is head, this is next, okay. So temp, that's just gonna point, okay, wait, head, next, next. So that's gonna point here. And then temp next, so temp next, that's gonna point to head next. So this no longer becomes a null pointer, and that's gonna point to head next and head next. Or it's gonna point to where head next points to, which is here. So there's no error, so that's fine. I should have put it in the box. It should be in the box. No, the whole thing. What is going on? There we go. No. There we go. Control X and then Control V. That should work. I don't know why it's blurry, but I'll just have to deal with it. Continuing after the previous 2 lines are run, the following code is behind it. So it's gonna. So head next next equals head. So head or head next next. So node 15. Wait, no, node next next. So this, that's gonna point. So it's no longer gonna point to node 15. That's gonna point to where head is pointing, which is 5. Okay, so far so good. And then head equals temp. So head is no longer gonna point to node 5. It's gonna point to where temp is pointing to. It's gonna be pointing to node 15. So what this code, I assume, is trying to do is it's trying to reverse the linked list, but the only problem is it forgot to get rid of that. For this question, use the following node definition, same definition. We're now interested in swapping the last 2 nodes of the list so we can end with the following. Fill in the blanks of the following statement of code. Can we try copy and paste? I can't. Oh no. Whatever. Okay. So we're just swapping 10, 15, okay. So node temp is equal to head, which is node 5, and then next, that's gonna point to node 15. Yeah, fine. And then head next. we want that to point to, let's draw it out. So head is going to be 5, null pointer, and then temp is going to point to head next, so temp. Point there. And then head next, we want that to point to 15, which is temp next, so temp next. So after that happens, this is only going to point to 10, this is going to point to 15. And then we want this, 15, no 15 is next, we want that to point to 10. So, temp, next, next, which is this. This is not going to be null pointer, this is going to point to temp. So here, to where temp is pointing. And now we just need to make temp next equals null pointer. So no 10 is not going to point to anything, it's just going to be null pointer. So it's the same, so yeah, head is 5, and that's going to point to 15, just like in this diagram. That's going to point to 10, and then it's going to be null pointer. Okay, good. Consider the following question that can add values on the link. So I've already done this. It's because this is passed by value. Consider the following recursive function. Whoa, what's going on? Current value plus 1 9 10 so the playlist. Already did that one as well. Okay. 24, your task. Your task with implementing a linked list class as in project 3 of the class. You have to implement a function called app that receives as input index and return the value that is saved at the node index node's length. For the first node is saved position 0 to second position 1 and so on. As a project 3, the linked list has two member variables, list size, list front, fill in the blanks, and the following implementation of the add function. So, if index is less than 0, or if index is greater than or equal to this size, we're going to throw an out of range exception, index out of bounds. Okay. So node cur, we want that to be at the list's front, so this. Underscore front. Size t equals 0. So while I is less than list size, no, while I is less than index, because we only wanted to iterate index number of times. And cur. So while cur is not equal to null pointer. So all you need to do is traverse through the linked list, so cur, not like that, cur equals cur next, and then we just implement I, and then we just return cur. That should be good. Two following binary tree. And really not. So in what order will the nodes be to the biggest thing? So pre-order is gonna process the node, then go left, then go right. So it's gonna go 5, then it's gonna go left, 10, then it's gonna go left, then it's gonna go left, 14. 14 is done, 11 is done, 10 is not done yet, it goes right, 12, then it's gonna go left to 18, 18 is done, 12 is not done yet, we have to go right to 15, 15 is done, 12 is done, 10 is done, 5 is not done, we still have to go right, that'll be 9, inward traverser or traversal, it goes left, then it processes the node, then it goes right. So 5, go left 10, go left 11, go left 14. Then we go to 11 and 10. And then all 10's descendants have to be processed with 5. And I'll be not 12 yet. We don't process 12 yet. As we do left this. So this will be 18, then 12, 16. Then we do 5. Okay, and then post-order traversal is go left, then go right, then process the current node. Okay. So 5, then we'll go 10, 11, 14. Then to 11. Then with 4, 5, 6, 10, go to 12, and 18. Process that. Then we process 15. Then we can process 12. Then we can process 10. Then 4, we process 5. We go all the way to 13. Then the 9. Then the 5. Starting with an empty tree, suppose that we add the following values to a binary search tree in this order, draw the resulting BSB after all insertions are complete. Okay. So 40. Start at 40. Then we insert 22. 22 is less than 40, so we insert to the left. Then we insert 58. 58 is greater than 40, so we insert to the right. 37. 37 is less than 40, but then greater than 22, so we insert to the right of 22. 37. 23. 23 is less than 40, greater than 22, but less than 37. 60 is greater than 40, greater than 58. 55 is greater than 40, less than 58. 68 is greater than 40, greater than 58, greater than 60. And then is a resultant BST and ABL tray? No, because the height of node 22 I think is, yeah, 22. No, 22. The height is left minus right, I think. So the height is negative 2. Which is not between Implement the insert function for a BSC class. This function receives a value as input that should be inserted to BSC. BSC's class only has one number, so there is no roots to affect the root of the tree. So it's just inserting a BSC. Okay, inserting into a BSC. To avoid insert t value, so we have to call the helper function. Helper value, and then we're going to use this root. I think it's called root, right? Yep. What is it returning? It's not returning anything, so this should be void. I think it should be void. And then this is going to be, oh, I need the type. So the type is just t value node pointer root, not root, cur. If cur is equal to null pointer, that's when we want to insert the node. So cur equals new node with value, and then else value, oopsies, else if value is less than and cur's value thing is just data, so it's cur data. We're gonna call the recursive helper function, so this insert helper value, and then call cur to the left, and else we're gonna call this insert helper value right. Line's optional, so implement function called equal trees that receive two binary trees when in terms of the two trees are equal. For example, in the following picture, root A and root B are false, root A and root D are false, but root A and root C are true. So there's just a bunch of base cases. Okay. So we're going to return true, I'm assuming they're both null pointer. So if root 1 is null pointer and root 2 is null pointer, we're going to return true because there's nothing saying that they're different. They're both null pointer. And then else if we return false. So let's say root 1 exists, but root 2 doesn't exist. Or if root 1 doesn't exist, but root 2 does exist. We're going to want to return false, or that means they're not equal. And then else if root 1's data, is it data or value? I think it's just data. Root 1's data is not equal to root 2's data. We're going to return false. And then else we're going to return else it's called equal to. So we're going to want to return this equal. Is this in a class? Not necessarily, so I'm not gonna use this. Equal to, we're gonna call root 1 to the left, and then root 2 to the left, and then equal trees, we're gonna call root 1 to the right, root 2 to the right. Yeah, that should be good. You have a hash table that stores integers into chain with lists. It's code handling mechanism. Hash table resizes from the low type to greater than equal to 1 by doubling the rate capacity. Third condoms the hash table resolves. Insert the following values into this hash table. 10, 34, 29, 39. So immediately we're gonna wanna resize that. So 6 is gonna go here. 18 is gonna go here. 3 is gonna go here. 19 is gonna go here. Then we're going to insert 10. 34. 29. 30. 99. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's less than 10. So we don't have to resize after that. Start from array blank 5 is probing. So before the first resize, start with an array blank 5. So this will be once it's 2. 1, 2, 3, 4, 5, 6. That'll have an index of 1. And A will have an index of 1 as well. And then before the second resize, so now the length is 10. This is when we have 4 strings. So 1, 2, 3, 4, 5, 6. That'll be an index 6. And A, that'll still be in 1. Then we have empty string, that'll be in index 0. And then 9, 8, 7, 6, 5, 4, 3, 2, 1. That has 9 characters, so that'll be in index 9. And then after all inserts, so we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, and we have AB. So 1, 2, 3, 4, 5, 6. That'll still be 6. A will still be 1. Empty string will be 0. 9, 8, 7, 6, 5, 4, 3, 2, 1. That'll be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That'll be also 9. And then AB. That'll be AB. Oh, it uses probing. Okay. So this is going to be in 2. Six, 1, 0, 9, that's fine. And then this won't be in 9. This will be in 10. So we're just increasing it by 1 because it's already taken. Sparky has been hired by a realtor. Okay, this is just a hash function. This is a good hash function. So the cell ID itself, yes, because it's unique. It's easy to compute. It's just the ID, nothing fancy. And good coverage because it's 9 digits long. There can be many IDs out there. The sum of the digits of sale ID? No, because it's not good coverage. The max is, well, if there's 9 digits, the maximum digit can be 9, because it's 0 to 9. So 9 to 9 is 81, so there can only be a max of 81. And the minimum is only 0, so it can only cover 0 through 81. And that's not good coverage at all. C++ defaults string hash function inside company. So company is not unique. So it's just not unique. Not a good hash function. So the default string hash function applied to address that is unique. And it's just the same as that. A new random number each time. No. Because it's not consistent. It's just random. In this question, we'll work on implementation of a set using a chaining hash table. Recall the chains can be any collected objects of list. Replace the these vectors. Complete the following class declaration. Implement the maybe size function now. Correctly define the hash table by doubling the number of buckets below factors above 1. So let's see. If we only want to resize if size, if the number of buckets below factors above 1. Okay. So if this as v is less than the bucket, not bucket, capacity. And once size equals this capacity, then we run the resize function. Resize to new capacity, equals, we're going to double the number of buckets, so it's just going to be this times 2. And then vector new buckets is equal to new vector with type kt, and then it's going to have new capacity number of elements. And we have a double nested for loop. So what is even in a bucket? Oh, it's a hash table. So for each bucket, and each bucket will have a link. Each bucket is a linked list. So for size t equals 0, n is less than this capacity increment a, and for each item in the linked list. So for const auto ampersand value in this, it's called buckets, right? This bucket access a. We're going to compute the index. So size underscore t index equals, we need the hash bucket, so hash t and then the key is, okay, wait, no, not using that, this is the key. And then new buckets, this is a vector, so we can use .f. New buckets, I should use .f for the other one as well, it's better to use .f in brackets. New buckets .at a, not a, .at equals we want to delete this bucket. We want to set this bucket to new bucket. And then we want to update this capacity. This capacity equals new capacity. Okay, looks good. Consider the following AVL tree. Ratio following inserts. Mention whether or not tree will still be an AVL tree. If it isn't, then you should mention it and I would know the tree is broken. There are 4 different inserts on the same tree, not 4 sequential inserts. Inserting 22. It's broken at node 40, so broken at node 40. After that, insert 59. It's not broken anywhere. So still AVL. Inserting 61. So it's going to insert here. That's still AVL. And then we're going to insert 75. Greater than 60, greater than 70. Wait, what? 75 or 65? 75. Greater than 70, less than 80, greater than 73. So it's broken at node 80. Oops. Because it has 2 nodes to the left, 0 nodes to the right. Consider the following AVL trees insertions of a different tree. In the first box, rotation. Inserting 11 and then rotating. I'm not going to draw the tree. I think that'll just take more time, but I'm confident that I know how to. So inserting 11 is less than 46, less than 49, less than 17, less than 12. Is it broken anywhere? Yes, it's broken at 29. So we're just going to do R on 29, and that should fix everything. Inserting 67, so greater than 30, greater than 42, greater than 55. Yeah. It's broken at 42. So we're just going to do left on 42. Insert 13, less than 17, greater than 7, greater than 11. So we're going to insert it there. It's not broken at 11, it's not broken at 7, not broken at 17, so no. Insert 33. It's less than 63, it's less than 40, it's greater than 20. It's not broken in node 22, it's not broken at 40, it is broken at 63. It's too much to the left, and then 33 is to the left of 40, so that's just a simple right on 63. Implement a function called isBST that verifies whether a given binary tree is BST. This function will see the root node of the tree as a parameter if return true if the tree is BST and false if it's not. So return isBST helper. This, not this, because it's in a parameter. So just root. So there's no this is not a class. Or not zero. So isBST helper. So if cur is null pointer, We just want to return true. That's the base case. And then we want to return false. Like this. Okay, so if cur if cur data is less than lower, or if cur data is greater than higher, we return false. It has to be between lower and higher. And then we want to return the recursive function is recursive case, so is bst helper we're going to do cur left lower and then cur data. That will be the max for cur left. And then is bst helper for cur right cur data upper. Oh, upper. So this should be upper. This should be fine. Spark is implementing our root main function that removes the node with the minimum values in bst and returns its value. Use bst there's only one member of it is root to keep track of root tree. Only part for no parent pointers, you break the following implementation. If this root is no pointer, I'm going to throw a runtime error at the end of the tree. I'm going to set parent to null pointer, I'm going to set cur to this root. While cur left is not null pointer, parent becomes cur becomes cur to the left. We're going to set rect to cur data. We're going to delete cur. We're going to set parent left to null pointer, and then we're going to return rect. Two bugs in the question will cause different sanitizer errors. Let's explain one bug. Drop BST will trigger this bug. So I'm thinking of all the edge cases. So one edge case I'm thinking of is just a tree with a singular node. So 69. So if this root is null pointer, it's not. So parent equals null pointer. Cur. So cur point here. And while cur left is not null pointer. So this while loop isn't going to iterate at all. So into rect we can cur data. So rect equals 69. We're going to delete cur. This no longer exists. Parent left equals null pointer, but parent is null pointer. So parent null pointer, but parent left equals null pointer. We can't do that because parent is null pointer. We can't set parent left to null pointer. So that's a bug. I'll explain one bug. So if the tree only has node, parent remain null pointer, setting parent left to null pointer is not allowed. And we're just going to draw a singular node with 69. Nice. Explain the other bug. Okay, what's the other bug? What's another edge case? I'm thinking a tree that only has right nodes. So I'm thinking, let's do 11 for Iota Sumo. Let's do 30 for Steph Curry. And let's do 77 for Luka. Wait, I'm not sure if it's the bug though, so let's just highlight it. Let's work this out. So parent equals null pointer. So let's get rid of this. I should have kept that, because parent equals null pointer. Cur equals this root, so cur points here. While cur left is not null pointer, but cur left is null pointer. So this while loop still doesn't iterate at all. So int ret is equal to cur data, so ret is equal to cur's data. Cur's data is 11, so ret equals 11. We're going to delete cur. That no longer exists. Oh, it's the same bug. So I think it never updates root, because root is still pointing to 11. But we need to point, what it should do is it should point to 30, but it's not doing that. That's the other bug. Okay. That's the other bug. This root does not. Let me double check that it doesn't. Yeah, it does not. Oh, it only does that for. It only does that for a tree that doesn't have left, or where the minimum root is the. Oh, that's the bug. This root does not update when the minimum value node is the root. Okay. Oh shoot. Oh sorry. Ah. Is the minimum. This question is about the worst case scenario for a chaining hash table. Draw a diagram of this worst case scenario. Okay, so running search. Oh, okay. So let's see. So the worst case scenario would just be we have index 0. Let's use a different color. I haven't used. Let's use orange. 1, 2. No, it starts at 0. 0, 1, 2, 3, 4. And the worst case scenario, let's use purple. Why not? Worst case scenario would be they're all in the same index. So 7. Oh, that wouldn't make sense. Almost was a 5. So 5, 10, 15, 25, 75, 35, 40, 0. Yeah, that's the worst case. What is then the worst case runtime search on the chain hash table? So that would just be O then. The long linked list. What is then the worst case runtime of insertion? That's just O of 1, because we always can prepend to any linked list. And prepending always takes O of 1, we just add to the front. Consider the following class declaration with a template of type name key class hash table, private, there's buckets, I see. I already did that. Okay, we can skip this. Sparky adds the following values in order to initially empty AVL tree 15, 20, 25, 25. He gets the following tree. Is this the correct result of the sequence of digits? Well, let's find out. So 15, done. We're going to insert 20. 20 is greater than 15, so we're going to insert to the right. Done. 25, we're going to insert, okay, 25 is greater than 15, so we go to the right. Greater than 20 means go to the right. But now 15 is unbalanced, so we perform a left rotation on 15. So 20 would take the place of 15. We're going to move 15 to the left, and then 25 would remain like that. So that would be our new AVL tree. 25 is done. Okay, now we're going to insert 10. 10 is less than 20, so we go to the left. 10 is less than 15, so we go to the left. Boom. And done. Then we're going to insert 5. 5 is less than 20, go to the left. 5 less than 15, go to the left. 5 less than 10, go to the left. And then node 15 is unbalanced, so we make a right rotation on 15. That means 10 would take its place. We move 15 to the right, and then 5 takes its 10th place, where it remains 10th left child. So 5 is done. And that's not the same as this. So no. Bro didn't what did he even do? Oh, bro didn't rotate when, which node was it? Node 25. Node 25 was inserted. Alright, I think that's it. Okay. So yeah, this worksheet was for a lab we had to do, where we only had to do 4 of these review problems. I decided to do all of them, because I knew it wouldn't take that long. And it didn't. Completed it in sub 2 hours time. I think that's a world record. I'm gonna save this. Waiting for it to finish saving. Then I'm gonna get a nice long rest.